Okay, so let's actually then, now that we are at it, let's just go over and look at basic material setup. My material basically uses the diffuse color for the picture that goes on the surfaces, and then it uses the emissive component, emissive channel, and the emissive channel is where I'm using basically the glow. And then the specular channel is kind of, it gives me the look on the bricks that look like they're a little bit damp, they are moist. So when you're looking at them, there's going to be a little shininess to them. So let's break these each and see how they are set up. Okay, is everybody with me so far? All right, so I'm going to actually take this and copy and paste each segment in your in somewhere that I can write on them, and then I'll explain how these work. Okay, so the biggest component here with this material is I want to create a diffuse color for my material. So this is what I'm interested in actually calculating. So how am I going to do that? I brought a texture sample, and this texture sample, what it does is basically it gets a picture, and the picture that UDK wants is in the format of Targa, TGA pictures, and they must be square pictures, and you can bring pictures that are like 1024 by 1024 or whatnot. Okay, so the pictures that I gave you when it came from the book, they have 4 channels. They have R, G, B, and A. What this means is that each pixel is represented by 4 values. An RGB value, which is basically how much red, green, and blue component that pixel has. And then it will also have an alpha channel, or an alpha value. And this alpha value ranges between 0 and 1. Okay? So basically, if you look at the RGB picture, that's the way that it looks is going to look like brick. And then if you look at the alpha channel alone, it's going to look like a black and white picture. Okay? So what I'm actually doing is that I use this the channel here, the black channel here, and this will give me all of the R and G and B values all together in the form of a vector 3. Okay? Basically, it's going to be each pixel is going to have 3 values, R, G, B, and R, G, and B. And if I directly plug this this RGB, if I plug this, where is my pointer? I lost it. There it is. So if I plug this in to my diffuse channel, my material is going to look a little bit dark. What I did actually by doing this multiply is that I took the RGB value of my pixels and then I multiply it by 3. Right? So I brought a constant here and I added value 3 or 4 or 5, whatever you want. And then you apply the result of this multiplication, which is 3 times RGB value at each pixel at location X and Y, right? So if you look at your material, you look at each face of that material, it's going to be at a given location, pixel-wise, ranging from 0 to 1024 and 0 to 1024 from either side. In fact, actually for the texture maps are going to range from 0 to 1 on U and 0 to 1 on V channel, right? So this X and Y, or U and V, in terms of their texture coordinate, each pixel will have a value. It's going to be multiplied by 3, and that is the color of that pixel of your material, okay? Then the specular value that the artist created, the black and white channel, if you look at it, then it's going to be kind of like a little bit brighter on the corners of these bricks, right? So let me just put these like white. So the corners of these bricks are going to kind of look brighter. and they would have higher values. And so when you plug this alpha channel into your specular value, basically it's gonna make your material kind of look a little damp on the sides of the bricks. So it's gonna, when you get really close, you're gonna see some reflectiveness on those components. So these two parts, the diffuse component and the specular channel, are what makes the look, the RGB look of your material. Is that clear? Any questions before I go to the next step? Sugarland? No questions? Should I move on? Okay. Now let's go to another step, and hopefully I am recording. Yay! Looks like I'm recording. Okay. Now look what happened here. The bump offset. So I dragged the bump offset material, and I fed the UV values of my texture sample from the bump offset. And what I did is I brought a texture sample with my normal map, and I used the RGB channel of that normal, or rather the alpha channel of my normal map as the height of the bumps on the material. Now, without this part, my material would still work. See, if I unplug this channel, the material still works. It's just if you get really close to this material, they're going to look like the areas that are a little bit kind of the crevices on the material. They're going to give you a 3D look, but not quite as far as I want it to go. So what the artist has done is, when they created, remember when I said they created the texture sample, they did the RGB for the red, green, blue color, and then they encoded the specularity of the pixels in the alpha channel, because the specularity ranges from 0 and 1, right? So they used that additional component in the same picture. They did the same thing. They actually added some extra height in the RGB in the alpha channel of the texture map, because the texture normal map has RGB values. That is, for each pixel is the vector where the normal is pointing out. So it's the coordinate of that vector out of the out of the normal map. What they did in the alpha channel, they also added some extra height, so that your normal map itself, the RGB values, make your material look 3D. But where you want to get a little bit more depth, they actually added that as an additional value. So what we are actually doing is that from the alpha channel of that map, we're going to add it to the height of a bump offset, and then we're going to offset our material a little bit more. See, do you guys see the difference between having and not having this this height map? Let me just redo this. See, this is how the material looks like without the additional bump offset, and so it kind of looks 3D. See, see here is the brick side, and then it kind of goes down and then goes up again in this ridge here, and same on this other side. If I turn the lights off, you're probably going to be able to see, you probably see better with this. Now when I add that additional height offset on my bump offset, just immediately you see that things kind of get the crevices get deeper. That is the additional bump offset that I have there. Okay, so that is the part that this bump offset does. So what I actually did is I created this bump offset for my diffuse texture map that is going up to the diffuse map, and then also I added that to the glow that I'm adding to my material later on. Okay, so now look at this normal map. Basically, I create a texture sample and I add to it the normal map, and I just drag the RGB channel of it to the normal component. So the normal map itself will give my material a 3D look. If I disconnect my normal map, my material is going to look very two-dimensional, right? So you would have to bring the normal map in the form of a texture sample and apply it to your to the normal channel of your fond material. Any questions with this so far? No? Sugarland? You good? Okay. Now let's take a look at my glow. I'm going to actually disconnect this glow altogether. This is how my material looks like without the glow. Okay, so basically it has the two-dimensional texture that is multiplied by 3 and applied to the diffuse color, the diffuse channel. A black and white picture is going to be applied to my specularity. See, if I undo my specularity, these highlights on the sides are going to go away, right? So that's what my specularity did. When I click this and bring this specularity and connect it to my channel, see on these sides of the brick, they're going to look a little bit shiny. That's what the specularity does. If you look at the alpha channel of my texture map, it's going to look black and white, and it's going to be wider on these areas that you're going to see the shininess. That's the specularity. And then I have this texture map, and your textbook may have 2 different texture maps for offset and your normal map. I used the same guy here, and I just applied it to my normal channel, right? So for the glow, I need to bring a color, and then I need to add that color in the emissive channel of my material. So if you look at this emissive channel here, whatever you give it, it will make your material shine that color. So let's see if I bring just a three-dimensional vector, and let's make this to be, I don't know, like 0 point, or rather let's make it 1.5 and just make it 1.5, a bright red color. If I apply this to the diffuse, then my entire material is going to look red. That's what diffuse does. Emissive does. Emissive shines a color. I really don't want my material to shine red all over, right? So what I'm going to have to do, see, if I do this red to the diffuse color, my material is going to look red, right? Since I wanted the material to look like brick, I brought a brick texture and I applied that brick texture to my material, so my material looks brickish. I'm going to do the same thing with the emissive color. The difference is that I'm going to work the textures that I have to get light values like green, red, pink, whatever your glow color is, to get those inside the crevices and then make the rest of that glow to look quite dark. How am I going to do that? It's actually kind of nice. Remember when I said that the guys who created this texture, normal map, they encoded the 3-dimensional vector values for each point in the RGB of your normal map? And then I told you that they also made the additional height offset in the alpha channel of the normal map, that then I used to make these crevices look deeper, to offset the bump, right? Now, it turns out that since I want the crevices to look shiny, I can use that information because the alpha channel of the normal texture basically has the crevice information in it as an additional height value. So if you look at these 2 texture samples, see, these 2 texture samples are exactly the same texture samples. The difference is that basically from this secondary texture sample that I have here with the normal map, I'm only using its alpha channel, right? So if I bring the alpha channel here, the alpha channel looks like this of my normal map. It looks quite bright. Okay, so if I don't think it zooms anymore. So if you look at how the alpha channel of the normal map looks like, it looks very, very bright. It's very, very whitish in the crevices between the bricks. And then on the surface of the bricks, it looks kind of lighter. It's basically darker. There's a slight problem though, and that is if I apply this directly, it's going to still look quite bright. See, if I drag this value and directly apply it to my emissive channel, my entire material is going to look quite whitish, because although the values in the crevices are bright, the rest of the material is bright as well. So let's take a look at this actually and see what we can do to make this look a little bit better. Okay, all right, and then I'm going to copy this in here. Then I'm going to show you how we work this out. All right, let's take a look at the alpha channel of my texture map. See, the texture map for the normal channel. This is my normal alpha. Okay, so the normal alpha comes in here, and this is how it looks like. So if you look at the crevices in between the bricks, they're quite whitish, and then the rest of this is pretty dark. The way that it actually is written, the texture, if you look at this pixel value, okay, so this pixel value, its value is going to be, let's call this I. So this I is going to be in the range of, say, something like 0.9, right? But if you look at this other pixel here, right? If you look at this pixel value, let's call this value J. This is going to be in the order of 0.1, right? So the brighter values are closer to 1, the darker values are closer to 0. So this whole normal alpha channel here, this value ranges between 0 and 1, right? So this basically is the darker sides, darker pixels, and the ones that are brighter, they're closer to 1. So these will be basically your brighter. Your brighter pixels, right? So we're looking at this. Now, what I'm going to actually do is I'm going to negate this value, and then I'm going to actually multiply, or rather raise that value to a high power. So this is the next step of the process that I'm doing. Okay, so I'm going to take this value here, and we're going to apply this. Okay, so we're going to apply this and raise it to a higher value. So these guys, these brighter values, these were closer to 1, and these guys, the darker values here, these were closer to 0. Okay, so let's just look at, like, make up a number. I mean, I could get that number from the texture value, but why not making up this number? Let's say that this value is quite bright. So if you look at this pixel right over here, so if I look at this pixel right over here, okay, this guy, its value is going to be 0.99. Or a value close to 1, because it's quite bright, as opposed to this guy, for example, the one right next door to it, right? If I'm going to look at this value, this guy's value is going to be something like, I don't know, 0.15, closer to 1, right? So I'm looking at these guys, this pixel here, okay, and then this pixel over here. Okay, are you guys following me? Just basically looking at two neighboring pixels here, and I look at those values, and let's suppose that those values are in this range, which they are, right? So if you look at 0.99 and 0.5, one is 0.99, which is quite bright, and one is 0.15, which is dark, but it's not really completely dark, or very, 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 very small. That's what makes the original alpha map kind of useless for us, because what we are interested are inside of these crevices, and we want the rest of this to be completely black, right? We want them to be very, very close to 0. How are we going to implement this? It actually turns out a very simple operation. The operation is basically a power operation. So if you look at this value, and let's say that this value is basically called alpha, okay? So alpha here is 99, and then alpha here is basically 0.15, right? So if I take this value and then I raise it to a power, and what I'm actually doing here, I'm raising it to a very high power, like alpha to the power 40, right? Take out your calculators and calculate these two values for me. 0.99 raised to the power 40, and then 0.15 raised to the power 40. What I'm actually telling you is 0.99 raised to the power 40 is going to be small, but it's going to be much, much larger in effect to 0.15 raised to the power 40. 0.15 raised to the power 40 is actually going to probably be very, very close to 0, and your calculator may not even give you the value for it. Whereas 0.99 to the 40 is going to be 0.8775 or something like that. Actually, I'm quite curious. Let's actually make these calculations, because I just made up numbers. Let's just... Okay, 0.99. 0.99 raised to the power 40 is 0.67, right? Whereas 0.15 raised to the 40 is going to be practically 0. It's 1 to the negative 33. So it's like a 0. So 0.99 raised to the 40 was 0.67, and then 0.15 raised to the 40 is basically a 0, and about 33 zeros, 1. Okay, so this operation, see, alpha channel raised to the 40 is going to give me this pretty neat looking black and white picture with white values in the crevices, exactly what I want them, and black pixels the rest of the images. So if you apply now the result here, see, here's what I'm going to do. If I apply the result of the power to the emissive channel, now all of a sudden my material is going to look like it's glowing white inside the crevices, and it's not glowing at all on the bricks, right? So this is what I got. The alpha channel here was basically 0 and 1. The crevices were 0. The rest of the picture was 1. I made a 1 minus operation to make it flip, so the crevices are bright and the bricks are dark. Then I raised that value to a high power to make the crevices still stay bright, and then the rest of the picture basically stay dark. And then that's actually what I'm getting for, or getting out of this operation. So is that operation clear? These 3 steps. I got the alpha channel of my normal map. I fed it into a 1 minus to give me this black and white picture right here. And then I raised the value of that to the power of 40, or whatever power you want, to give this other color. See, here if I change the power to 1, that's the original alpha channel. See, if I raise it to say 5, then it's going to suppress some of the dark, but not all of the dark. If you raise it to the power 10, then it's going to suppress more of the dark. If you raise it to the power 25, it's going to even suppress more of the dark. And I just like the 40 because it just makes the inside of the crevices shine and make the rest of the picture untouched. Okay? Sounds good so far? Sugarland, do you guys like this idea so far? Any questions? Who didn't like this calculation? Raise your hand. Who liked this calculation? Raise your hand. Just one? Alright. Just 3. There is so many of you out there. Okay, tell me what part is confusing and what part you did not like. I'm not going to move forward before I know what part you did not. What part you did not like?
I have one question.
Go ahead.
On the copy for the bottom texture sample normal map,
This one.
whenever you drug the alpha channel into the 1 minus, is that what made it invert colors where the mortar was white and the brick was black?
Yeah.
It normally would have been the inverse of that.
Yeah. See, if you look at it and how would, let's actually do this. Let me just drag this alpha channel and drag this to your emissive. The original alpha channel looks like this. It's actually the opposite. You see, the original alpha channel of the texture, it's dark in the crevices and it's bright or closer to 1 in the rest of the brick. I didn't like that because that's not going to help me. It's going to make the bricks glow, not the inside. I wanted the inside of the bricks glow. So what I did is that I just inverted that value. I just put a 1 minus operation. So whatever goes in, it's going to, if you look at these two sides side by side, okay, and then I'm going to make this a plane. Okay, so the original looks like this. When you do 1 minus, it's going to look like this other one. So the crevices, the mortars are going to look brighter. And then I raised that value to a huge power to make it even more suppressed. Okay, Sugarland, did you guys like this question idea or the way that the calculation worked?
So raising it to a higher power reduces the intensity between the bricks?
What it does, the way that it works, when you raise a number to a power, and if the ranges are between 0 and 1, it's going to make the ones that are small, like 0 to 0.7 or something like that, 0.47, something like that. It's going to make them suppress them and get them closer and closer and closer to 0. And then the ones that are higher and closer to 1, it's going to make them still stick closer and closer to 1. If I attempt to draw it, actually, if I attempt to draw the values, this is, let's say that this is x, and this is x to the power alpha. Okay, and so we're interested in x ranging from 0 to 1. Okay, so what is going to happen, the equation is going to look like this. Let's start from alpha equal 1. If alpha is equal to 1, actually let me just make it blue for alpha equal 1. So alpha equal 1. Your equation is going to look like this. Well, this is my best attempt at a straight line, so don't hold me. Oops. Okay, so this is my attempt at straight line. So what's going to happen is that your when alpha is 1, what you have as input x is going to be your output too, right? So see, 0.2 is going to be 0.2. 0.5 is going to be what? You guessed it, 0.5, right? Now let's raise the alpha. Let's do alpha equal to. Actually, let's go back to this blue and let's do 0.75 too, right? 0.75 and 0.9. Okay, so 0.9 is going to be 0.9, and then 0.75 is going to be 0.75, right? Everybody with me so far? Okay, now let's change the alpha to 2. So if I do alpha equals 2, it's basically going to raise or make the square of x. So 0.2, original 0.2 is going to be what? 0.04, right? So 0.2 is going to be 0.04. So this is going to be 0.04, and this is going to be 0.2. 0.5 is going to be 0.25, right? So it's going to go somewhere here, 0.25. Then 0.75 is going to be 0.40 something, 0.49 something something. So 0.75 is going to be 0.49. So right here, 0.49. And then 0.9 is going to be 0.81. So 0.9 is going to be still a little lower. So, and then 1 is going to be 1. So your function is going to look something like this. As you see, it's going to suppress, even with the second power, it's going to suppress the smaller ones to make them look smaller and smaller, while keeping the larger ones stay larger and larger. If I do alpha equals, if I can find my pointer, if I do alpha equal 10, okay? So 0 to the 10 is going to be still 0, right? That's that. And 1 to the 10 is going to be still 1, so that's there. 0.9 to the 10, who can tell me what it is? 0.9 raised to the 10. Okay, 0.9 raised to the 10 is going to be 0.348. So 0.9 is going to be somewhere 0.348. So it's going to be somewhere here, right? So this is going to be where the 0.9 goes. Now do 0.5 and let me know what 0.5 is. It's going to be very, very small.
0.000976.
Awesome. So you see, I already suppressed even values that are closer to 0.5. So it's going to be 0, 0, 0, so practically close to 0. Now let's do 0.99. See, 0.99 stuck around, right? 0.94. So if I do 0.99, which is up here, it's going to be closer to there. So with alpha to the 10, my equation is going to look like this, right? So by raising those values to a high power, I made the darker values just to vanish directly. Just all of them to become very, very close to 0. Whereas the values that were brighter and closer to 1, they stuck around to close to 1. So that's how it looks like when I get, when I look at this, these values that you see they're bright, they were the ones that were close to 1. They were like 0.9, 0.99, 0.995 or something like that. And then the rest of this picture, the colors are basically quite suppressed. So raising to a power is your way of suppressing small values while keeping the larger values. And this is how the equation actually looks like. Not this one. This is how your equation looks like. So raising to the power 1 basically keeps the value. Raising to the power 2, it suppresses the smalls and keeps the large. And then keep increasing your power, it's going to make your equation kind of, if you look at it, it's going to look kind of like a needle, right? So when you increase your alpha, you're going to make your curve kind of slimmer and slimmer around 1, and then keeping everything else close to 0. Okay, so then what I wanted to do is actually I wanted to get this color. I didn't want it to look white, so I just wanted the glow color to look kind of greenish. So what I did is that I multiplied that crevice values that I did, multiplied it by a green RGB color, and so it made it look green. And then I wanted it to kind of glow brighter, so I even took that value and multiplied it by 9. So if I get this multiplication by 9 times the color is going to look more bright. And I like this because it kind of looks like lava shining from inside, although it's not really lavish. So let's just change this to orange or something. Lava-ish. There you go. Do you guys like this color? Yeah. Okay. Okay, right? So that's that. So I took the alpha channel, multiplied it by or inverted its value, so the crevices are brighter. Then I raise it to a power to make just the crevices bright and the rest of it stay dark. Then I multiplied it by an RGB color to make it to give it a color, and then I multiplied that color by a large value to make it shine. Okay, so this piece is the piece that made the crevices glow. How does that look so far? Any questions? So this is the piece. This is the piece that made the crevices glow. Any questions? Should we have a quiz on it?
So the function is just like cutting a parabola down its line of symmetry?
Yeah, exactly. And the symmetry is 1. No questions? Okay. So next is when I wanted to make the color to go between completely dark to completely this glow color, right? So let's take a look at this, and then let's just take this, and then I'm going to explain this to y'all, just this part of it. Okay. So now I'm going to make this glow go bright and dark. And what I have here, and I'm going to make it this color. So what I have here, this guy is my lava color. Right? So what I need to do is I need the output of this guy right here, to be between 0 and lava color, because that makes it glow. When it's 0, it's going to be dark. When it's full lava color, it's going to glow the lava color I want it to do. So that is the trick here. This multiply guy is going to take the lava value and then multiply this by some value that goes from 0 to 1. Okay, so this is the trick. To multiply the lava color by some value that by time it goes from 0 to 1, back to 0, back to 1. The good news is that we have the sign. We have the time element. Okay, and if we plug this time element and calculate its sign, okay, the sign of time, this is a function that looks like this. Let me actually make this dark so you'll see. So sign of time goes from 0 to -1 to +1 to -1 to +1 to -1. So if I directly take the time element, plug it into sign, and multiply it by my lava color, I'm going to get between negative lava color and positive lava color. Well, the problem is that we only really like the negativeness of it. So what I did is actually then I'm going to go in here and take the time with the frequency, multiply them, feed them to sign so that I can control the speed of the between negative and positive, and then make a function whose value is going to be 0 to 1. So how do I do that? It's actually quite simple. So you're going to get this, and this equation does that for you. So you multiply the time, multiply it by C, C is this guy, and then feed this to your sign. And this guy is going to give you -1 and +1. So it fluctuates between -1 and +1. And then what I'm going to do is that I'm going to take this and then multiply it by this other guy. So in here, I'm going to go between -0.375 to 0.375, right? And then I take this 0.375, I feed it to the 1 minus, so this guy is going to be 0.625, right? And then I add these two, which makes this number to go from 0.5 to 1. So that's the value here. And then when I multiply this guy by my lava color, I'm going to go between half lava color and full lava color, right? So if you wanted to go between 0 and 1, you would basically work with this guy here and this guy here to make your equation to go between 0 and 1, or whatever value you want. Sine gives you -1 to 1, and then when you play with these values, you're going to be able to change it from whatever minimum value you want to whatever maximum value you want. And then you'll take this value, see the result of this add, and then you multiply it by your lava color. So the result here is going to be making the lava color that you've got there, it fluctuates between the two values that you are interested in. Okay, and then all you're left to do is just to plug this fluctuating between small or rather half lava to full lava glow, and that makes your material glow. Any questions with this? Are we all good? How you plug and play these little modules to create a complex equation? So who can tell me actually in terms of if you're looking at, well, I have to ask this question. I'm sorry, but I have to ask this question. If you look at the pixel value, let's call this pixel value alpha, that comes from your normal map. Okay, let's call it alpha of x and y. And then let's suppose that your time parameter is t. Okay, who can tell me what is the emissive color of x and y based on the time, the alpha, and also the let's call this RGB color. It's the lava color. Okay. And this is your equation. This is your time. This is your alpha, x and y. And this is your lava color. Should we work it together? So I took my alpha, and then I calculated 1 minus alpha, and then I raised it to the power 40, and then I multiplied it by the RGB value for lava. And then what I did is that I multiplied this value by sine of c times t multiplied by 0.375, and then I added this to 0.625, and then I multiplied that value by the total color, and so this will become my emissive of x and y, if this guy is alpha of x and y. Do you guys like that? Or you hated it? Who liked it? Matt, you should like it too. No, I'm just kidding. You're indifferent? Who's indifferent to it? No way. You can never make a cool looking material. No, you could. But this way you'll feel something about it too. Any questions? Yes, no? Okay. Okay, sounds good. Let's see. No questions, really? Okay. Sugarland. Would this be useful to put it on Blackboard, Victoria? You wanted to revisit it?
Yes.
Something we can definitely return back to in the project.
And this is going to be a good segue to your to the next sets of tutorials. So with the find condition, basically what I'm trying to say is that with just the emissive channel, you can create a material. How are you going to be able to do that? A find lighting condition requires a diffuse lighting model that basically shows the reflection of light on the surface, a specular model that shows the focused reflectivity of the light, and then a normal channel that basically takes care of the calculation of your material. So if you have a light source like this, I call it LS. This light source is going to emit lights, and these lights, I'm interested in this pixel value, and let's call this pixel value X and Y. This is going to be the location of the pixel value. So when the light comes in, I have actually 3 rather interesting vectors that I'm going to be looking at. One important vector is the vector at which the light hits my surface on the point that I'm looking at. So I call this light vector, or LV. Another vector, and I draw this with red, it's basically the normal vector, and I call it NV. Okay, and finally there's another vector here, and I'm going to use this purple color, and this purple color is going to be viewer vector, basically where I'm looking at, and we call this C sub V, or camera. Okay, so to calculate light by find model, I need these 3 vectors: the normal vector, the light vector, and the camera vector, or the viewer vector. Okay, so how is it going to work? The calculation is made of 3 components: an ambient component, so the light that I see, the amount of light that I see that is reflected, is going to be made of a diffuse channel, and the diffuse channel requires the light vector to calculate, plus a specular channel, and the specular channel requires the light vector, the normal vector, and the viewer vector to calculate, and an ambient channel. Ambient channel doesn't require any of these values, right? So when you're creating a material, basically in Unreal, the camera is where you're located. So if you look at this material editor here, see wherever I am located when I move around, the angle that I'm moving around, this is basically the angle of me as the viewer, or the camera vector. Light by default is going to be at 1, 1, 1 location, and X and Y and Z in Unreal. So light is going to be always coming from this direction. So we also know the LV. And then the normal map, the guys that I have here, they are going to give me the normal vectors for my material. So by looking at my material, looking at the normal map of my material, so this N sub V comes from your normal map, right? The value of the diffuse color that you got here, it comes from your texture. Okay? And same with the specular value that you got here. So those values come from the texture. So when I calculated my find lighting model, I got this guy and I plugged it into the diffuse model. I'm good. Then I got the alpha channel of this guy, and then I plugged it to my specular model. So that gives me the specular value for my lighting channel. And then I also dragged this RGB value and I plugged it into my normal channel, and I was good. So my material looked 3D. To make my material glow, I just created this ridiculous equation, right? And then I plugged it into my emissive material. Emissive channel makes your material, makes that much light come out of your material at any given point and come directly to your eyes, which is the point that I'm trying to make. See, all these values that you're calculating here, all these values are going to come to your eyes through your camera vector or your viewer vector. So if you just forego of all these stuff from emissive, ambient, and specular, you can replicate it. I mean, diffuse, specular, and ambient. You can replicate it by looking and remaking these components of your light, by remaking them and just plugging them into the emissive channel. Because the emissive channel is exactly that much light that you give to emissive channel. It's exactly how much light goes directly to the viewer's eyes. And so by rewiring a big, massive chunk of equation, plugging them into your emissive channel of the material, in essence, you are going to make your material look exactly the way you want it, without the need to plug anything to its diffuse channel or anything to its specular channel or anything to its normal channel for that matter. Right? So the next set of equations, which is actually a good segue to complex materials, is doing exactly that. It's going to walk you through step by step, creating a material that you can do like ridiculously interesting stuff with. For example, make your material look darker and darker as it goes farther and farther from you. You can't do that with diffuse channel because diffuse channel gives a constant vector, a constant texture. You can't do that with normal channel because normal channel gets a constant texture. You can do that by writing an equation that takes that texture and multiplying it by the distance, how far or close it gets to the viewer, and then plugging that into your emissive channel so that your material shines that texture. And as you go farther and farther, the material shines lesser and lesser, so it becomes darker and darker. Okay, so go ahead and work on. I think the pinwheel is uploaded, and then what you're going to do is that you're going to bring constant parameters. Make sure that you change the name of the parameters, because if you keep the parameters the same name, they're called none. When you change one value, it's going to change the other one. So go and take the steps on tutorial 611 through 611 and 612. So basically, in your content browser, you're going to have to create a new material. And then and then give the name math underscore your name distance material or something like that, so that I know whose files I'm dealing with. And then drag in the two parameters for your colors, and then a linear interpolation that interpolates the values between 0 and 1, and then feed the value of your pixel distance or pixel depth, I think it's called. Again, so Sugarland and Victoria, just let's take a look and see what I've got here. Actually, let me just write this on board for you all. Okay, so do you guys, Sugarland, see this? Just going to explain this as we go along. Okay, so what I've got here is I've got my maximum color, it's like a pink color, and then no color. And then what I'm doing is that I'm using the LREP. LREP stands for linear interpolate. So what it does is that the alpha value of the LREP ranges from 0 to 1. And then what it's going to do, it's going to multiply, like when the alpha value is 0, it's going to get full color B. And then as alpha value ranges from 0 to 1, when it reaches to 1, it's going to make full color A. So basically, if you look at this and call this alpha channel as alpha, then the output of the LREP, this guy, let's call it output, is going to be A times alpha plus B times 1 minus alpha. Okay, so when alpha is 0, there's going to be nothing from A and everything from B. When alpha is 1, it's going to be everything from A and nothing from B. And when alpha is between 0 and 1, it's going to be some from A, some from B. Is that clear for y'all? So that's what LREP does. So when alpha ranges from 0 to 1, it's going to start mixing, like think of having two different paintbrushes. When alpha value is 0, you're going to just dip it into the lower color. When alpha value is 1, you're going to dip it all in the fuller color. And when alpha value is something between 0 and 1, then you're going to dip a little bit in the lower color or a little bit in the upper color. Right? So that's how you mix and match these values with each other. So if you drag the pixel depth directly to the LREP alpha, then pixel depth ranges from 0 to like a lot, right? So which means that when you're very, very close to the camera, you're going to see black. When you're very, very far from camera, you're going to see a different color. So I'm going to divide the pixel depth by 3000. So I'm going to basically make this range from 0 to 3000, right? Make sense? So 0 is going to be 0 and 3000 is going to be 1. And then I'm going to have a huge range to play with. And then that is going to make sure how much color from what side I'm going to get. Cool? Okay.